look for the critical point and see how the function is behaving before the critical point and after the critical point actually. If the function is, for example, if the derivative of the function is negative before the critical point, okay, that means that before the critical point the function was decreasing. And after the critical point, if the function is if the derivative of the function is positive, okay, then you're gonna say that yes, after the critical point the function has has started increasing actually, and so on and so forth. So the increasingness and decreasingness of a function can be understood completely through what do you call through the derivatives actually. So here's a let's put this in the form of a remark actually. Let's not make a box. It's like as it is. So if derivative of a function is positive on an interval, okay, then on that interval function is increasing. Okay, so the positiveness of the derivative tells you that the function is increasing on the given interval. And if f prime of x is negative on what do you call the given interval, then the function, okay, then the function is decreasing. Decreasing, and then the function is decreasing. Okay. So just compute the derivative and see on what interval function this derivative is positive and on what interval the derivative is negative. So the interval where the derivative is positive, the function is going to increase. The interval where the function derivative is negative, the function is going to decrease actually. And keeping in view, and obviously the points where the derivatives are zero are going to be the critical points actually. Okay. Now, just knowing that where the function is increasing and where the function is decreasing, you can already have, you can what you call make a sketch of the curve, roughly make the sketch of the curve. If in addition you know that the critical points are maximum or minimum, you can even what do you call make even better assessment about the curve, and you can sketch it actually. Okay, so the curve sketching can be done if you know on what interval function is increasing, on what interval function is decreasing, and what are the critical points. You can make a sketch actually. For example, let's make a sketch. So imagine I have a function f of x, okay, that goes like this actually. So 3x power 4 minus 4x cube minus 12x square plus 5. Okay, plus 5. Now if you compute the derivative of it, okay, you will face an interesting situation that you will have 12x cube minus 12x square minus 24x. You can already see that you can easily factorize this function. If you say, for example, take out 12x, so you're going to get what you call x squared minus x and minus 4 actually, 2. And you can even factorize this, and you're going to get 12x times x minus 2 times x plus 1. Okay, so this is the derivative of the function actually. Now I want to know that on what point the function is increasing, on what intervals function is increasing, and on what interval function is decreasing, and on what interval or on what point the function has critical points actually. And then I want to make a rough sketch of it. Now, obviously, if f prime of x can has these critical points, has this form, then the points where f prime of x is 0 are going to be what? So if you substitute, say, x equal to 0, f prime of x would be 0. If you substitute x equal to 2, your function would be 0, f prime of x would be 0. And if you substitute, say, x equal to -1, your function would be 0. Okay? Your function would be 0. Now, why these critical points are important? Because, you know, before and after this critical point, function is either going to change its behavior or not actually, because some critical points can be inflection point as well. So what is the best way to do this? So take your, for example, xy axis, okay, and see where is -1. So let's say that this is -1. Where is 0? So this is 0. And where is 2? So 1, and say this is 2 actually. Okay? This is 2. So now all intervals, so if you for example take this and these points, okay, then all intervals, so these intervals are the intervals where you have to really take care of it. That how the function is going to behave in this interval. In other words, intervals within the pink points, here, here, and here actually. So in other words, I would say, and I can summarize this in the form of a table actually. Okay. Obviously, to know that when the function is increasing and decreasing, you need to know the sign of f prime of x actually. Okay. So keep the factors here. So this is x, say x minus 2, and say x plus 1 actually. Now, when f prime of x would be positive, now you have 4 numbers actually. When these 4 numbers are multiplied with each other, then it depends. I know that 12 is positive, so that means that positivity of f prime of x depends on these 3 actually. And there can be various possibilities. Imagine these 2 are, so this is positive and this are negative actually. Then plus multiplied by minus multiplied by minus is going to be plus actually. So outcome would be positive. So the other possibility could be that, okay, this is negative, this is positive, this is negative, so on and so forth. Okay? So in other words, whether f prime of x is going to be positive or negative depends on these 3 factors. So therefore I'm making a table of these 3 factors actually. Okay? And here I'm putting f. And here I'm going to put the intervals. Okay, intervals. As I said, which intervals are the intervals interesting? You know, the intervals between what you call pink points and these intervals actually. So what is this first interval? So you're going to say this is the interval that starts from negative infinity and say ends at -1 actually. I know at the -1 the function has a critical point. What is the other interval? Say between -1 and 0. What is the other interesting interval? Between 0 and. So you have to think between minus infinity to plus infinity. So in other words, find the critical points and then put what do you call these critical points on the real line, okay, and then what do you call consider the all intervals that has been created due to putting these, for example, big lines. So that's what you have to always do. So this is 0 to 2 because this is 2, okay, minus 1, this is 0 and this is 2 actually. And the final is going to be 2 to positive infinity. 2 to positive infinity. Okay. Now here's the interesting thing that you can conclude from here. Now if your x is a number between negative infinity to minus 1, so take any number that is between negative infinity and minus 1. So imagine I'm taking, say, x equal to minus 2. I know that minus 2 is going to be here. And substitute minus 2 here actually. So if you're going to substitute minus 2 here, this x is going to be negative. If you're going to substitute, for example, minus 2 here, x minus 2 is also going to be negative. And if you substitute minus 2, for example, in this interval, so this number is also going to be negative. And it's not just true for minus 2, you can put minus 2.5, you can put minus 3, minus 4, this would happen actually. Now, f prime of x is what? Is x multiplied by x minus 2 multiplied by x plus 1. So in this interval, x is negative, x minus 2 is negative, x plus 1 is negative. So what would be the product of three negative numbers? What would be the product of, what do you call, three negative numbers? Let me put, say, f prime of x, and then have a column for what do you call that. What would be the product of three negative numbers? So minus minus plus and plus minus minus actually. So the sign is negative. Okay? In other words, when x is negative, x minus 2 is negative, x plus 1 is negative, f prime of x will also be negative actually. Now if in this interval f prime of x is negative, tell me what is happening, what kind of behavior f is going to show. You're going to say f is decreasing actually. F is decreasing. Okay? Now if f is decreasing, what do you mean by decreasing? So in other words, thing is somewhere up and then decreasing means that it's coming down actually. So in other words, in this interval, you know, the curve maybe would look like this actually. So this is one of the possibilities that, okay? It's decreasing. Alright? This is one of the possibilities. You can have other way around as well, but you know, this is one of the possibilities actually. How about if I pick a number between, say, negative 1 and 0? Okay? Negative 1 and 0. Say, let's take, say, x equal to negative 1/2 actually. So, if x is negative 1/2, x is already negative. If x is negative 1/2, x minus 2 is negative, so this must be negative because minus 1/2 minus 2 is going to be a negative number. And if x is minus 1/2, for example, then the minus 1/2 plus 1 is going to be 1/2, that means that is a positive number. Positive number. That means that in this interval, the function is minus times plus, the function is positive. Because minus minus plus and plus plus plus. So in other words, the function is increasing in this interval. I know that this is a critical point where the function has started going up, but maybe the function is increasing actually. I don't know, where would it go? I'm saying that justice increases actually, goes to some point. How about if I now choose a point between 0 to 2? So what would be the point, for example, between 0 to 2? So let's take 1 for example. So 1 is a positive number, 1 minus 2 is going to be a negative number, 1 plus 1 is going to be 2. So it's a positive number. Okay? It's a positive number. So I have 2 positive numbers and 1 negative number. So what would be their product? So its product is going to be negative, and hence the function is decreasing. So what can I say about this function? Okay, it goes up and then comes down. Okay, something like that. How about on last interval? So if I choose, for example, x equal to 3, okay, and I substitute here 3, so this is going to be a positive number. You can choose any number actually from the interval. So it's not necessary that you should choose 3, or so you can choose 2.5, something like that. So I'm just choosing that number that is simple to verify actually. So positive, 3 minus 2 is positive, 3 plus 1 is also positive. So that means that f plus is positive, and hence the function is increasing. So what does this mean? This means, okay, so this is not between 0 to 1, but this is between 0 to 2, the function is increasing. So from 2 to infinity, the function has started increasing again, so maybe the function would go like that. I don't know, the function would go like that. Now if you will plot this function, you will see that its rough sketch is going to be something like that. Something like that. So on and so forth. Okay. So, if you want to find, know that when a function is increasing and when a function is decreasing, for example, especially about polynomials, factorize it and see what the factors are in the different intervals actually. And how to determine those intervals, see where the f prime of x is 0. Then split your real line into 3, 4, whatever parts, and then in each interval see what happens to each factor. Okay? And try to determine the sign of f prime. So if the f prime is positive in that given interval, you're going to say that your function is increasing, and if it is negative, your function is decreasing, and if it is, and hence actually, obviously if it is 0, then you are at a stationary point actually. Okay. So this is one of the first things. So I hope you have some sense of increasing and decreasing. Now I would like to come to another interesting topic, which is a very interesting way of finding which point is a maximum point and which point is a minimum point on a given curve actually. It will determine all maximum and minimum point, local and absolute and global as well. Okay, all points. Closed interval test just tells you the absolute maximums and minimums. It doesn't tell you global maximum, local maximums and local minimums actually. Right? This test can tell you all maximums and minimums actually. Okay. Before writing this, I would like to again what you call make an intuition actually. So think about these curves. So imagine I have this curve, and say, imagine I have this curve that goes like this, for example, and imagine I have another curve that goes like, for example, this, and say I have another curve that kind of goes like this actually. Okay. Now I have some function, 4 functions, and I want to know that, and I want to create a criteria actually, that how to decide that if you know the critical points of the function, how to decide that this critical point is a maximum or a minimum, or it's neither a maximum or not a minimum actually, it's an inflection point actually. Now I would like to relate this with the observation that we made previously. Imagine you throw a ball up at you and it gets back down. Okay? So you throw the ball, comes back. If it comes back, that means that this is an evidence actually that there must be a point, a maximum height where that ball reached, stopped, and then get back actually. Okay? Where it reached, above at a maximum, okay, stopped, and then reached back actually. So in other words, first it was going up, okay, stopped, reached to the maximum place, and then came down actually. So that would be a situation like that. Now tell me, if this is the critical point actually, or the maximum value of the function, what is happening before the maximum value and after the maximum value to the derivative or the curve actually. So the before maximum point the function is increasing, and after the maximum point the function is decreasing. So in other words, before, if you look at the the derivatives of the slope before the maximum point, they are going to be positive actually, they are always positive. No matter where you draw a tangent line, your tangent line is always going to have a positive slope, okay, positive slope. And after the maximum, your tangent line, wherever you draw a tangent line, is going to have a negative slope actually. In other words, a point is going to be maximum point, a critical point is going to be a maximum point if before that point f prime of x is positive, derivative of the function is positive, and after that point the derivative of the function is negative actually. So it makes complete sense actually that, okay, you have thrown something up, reached to the maximum point, and then comes down. So first, increasing, and then, the curve is decreasing. But how about this time now you throw a ball, for example, on ground actually. So first it will go down and then it will go up actually. So in other words, I'm going to say that this point is a minimum point. Why? Because before that point the function is decreasing, and after that point the function has increasing actually. So in other words, before that point the function has negative slopes, and after that point, no matter what point you choose, the function has positive slopes actually. So that before that point function was decreasing, and after that point function is decreasing. How about these two curves? Now these two curves are interesting. So if I, for example, take a point, at this point, the derivative of the tangent is 0. But the trouble with this critical point is that if you look at the tangent lines before that critical point, they have a positive slope, okay? But if you look at them, look at the tangent lines after the critical point, they are still positive actually. They are still positive. So what does it mean? It means before this critical point the function was increasing, and after this critical point the function is still increasing actually. So you're going to say this does not have max are minimum actually. So this is a point to which you will say this is a point of inflection. Point of inflection actually. And similarly the case is here actually. Think about it. So critical point, before that critical point the function has a negative slope, so the function is decreasing. And after that point, no matter what point you choose, the function is still decreasing because at all points the function has a negative slope actually. Okay? So in other words, if you have an abstract function, okay, you have to look at the derivatives. So a point would be maximum if it is first increasing and then decreasing after that critical point. Increasing, stop decreasing, so that would be a maximum point. Minimum, decreasing, stopped increasing, so that would be a minimum point. And if it is increasing and still increasing and decreasing and still decreasing, you're going to call it, they are the inflection points, are the points where you don't have maximum or minimum actually. So what we're going to do, so let's put all these observations in the form of a theorem actually. So this is called the first derivative test. First derivative test to find maxima, minima, and point of inflection. Okay. So it goes like this. So suppose C is a critical point of f of x. So it's a point where the derivative of the function is 0. Okay. So the first point, if f prime changes its sign, in other words the derivative changes its sign from positive to negative, okay, from positive to negative like this, then x equal to c is a maximum point. A maximum point. What is in the next point? So again, if f prime changes its sign from negative to positive, okay, around C, at C, then x equal to C is minimum. Okay. So the third possibility is that if f prime does not changes its sign actually, does not changes its sign at C, okay, in other words before C, say the function was increasing, and after C so still increasing, or before C the function was decreasing and after C it's still decreasing, then you're going to say f has, by the way, these maximums are going to be the local maximum and local minimums. Local maximum and local minimums. Then f has neither max nor minimum at C. Okay, so you call such points as the inflection point actually. Okay. Now, keeping in view the previous example, I mean, if we make, for example, that graph again quickly.